acknowledge. Whenever 8085 receives an interrupt, then it sends a output signal, that is interrupt acknowledge signal. Trap is non-maskable, all other interrupts, 4 interrupts are maskable. Then we have interrupt request. It is called interrupt request, INTR. It is of the lowest priority. The INTR is enabled or disabled by software. We can enable INTR, can be enabled or disabled by a software. Then we have low order address bus, that is AD0 to AD7, multiplexed address oblique data bus. These signals are bidirectional. These are time multiplexed address and data bus. During first clock cycle, it will carry address. After that, it will carry data. Then we have VSS. This pin is grounded. After that, we have high order address bus, that is from A8 to A15. It is unidirectional. Then ALE, address latch enable. S0 and S1, these are the two status signals. ALE, address latch enable, is an output signal used to demultiplex the address and data bus. In other words, ALE is used to separate AD0 to AD7 to address bus, that is A0 to A7, and data bus, that is D0 to D7. It becomes high in the first clock cycle of each machine cycle. When it becomes high, it indicates that the contents of low order address bus is address. When ALE is low, it indicates that the contents of low order address bus is, that is address oblique data bus is data. Then we have S1 and S0, these are two status signals. These tell about the type of operation. When these signals both are low, 0 0, then means halt. If S1 is 0 and S0 is 0, S1 is 0 and S0 is 1, then write operation. If S1 is 1 and S0 is 0, then read operation. If both are high, that is S1 and S0 both are high, then opcode fetch operation is performed by 8085. After that, we have input output oblique memory pin. If signal on this pin is high, then it indicates that the operation is related with input output device. If signal is low, then it indicates that the operation is related with memory. Then we have ready. Ready is an active high input control signal. With the help of this signal, microprocessor checks the readiness of peripheral device for data transfer, that is whether the peripheral device is ready to receive or send data. If the signal on this pin is high, CPU will perform data transfer. If signal on this ready pin is low, CPU will enter in wait state. After that, we have reset, that is reset in. Reset in is active low signal. Whenever signal on this pin is low, then microprocessor is reset, that is its program counter, hold acknowledge and interrupt enable all are disabled. Program counter comes at 0 0. Then clock out, here 3 megahertz signal is available. Then hold and hold acknowledge, these two pins are used with direct memory access. Whenever hold is high, hold is active high input signal, hold acknowledge is an active high output signal. Both signals are used to implement DMA data transfer technique. Signal at hold pin indicates that another device is requesting for the use of address and data bus. After the reception of hold signal, microprocessor completes the current execution. and then transfer the bus's control to other device by sending hold acknowledge signal. Then VCC signal, here we connect positive 5 volt supply. This is the signals or various pins shown in groups. These are serial input output control signals pins. Then we have interrupt control unit interrupt pins. After that we have DMA request, DMA signals, DMA status signals, hold and hold acknowledge. After that we have address buses, high order address bus, low order address bus, that is bidirectional address. Low order address bus is multiplexed with data bus. Then we have address latch enable, S1, S0, these are two status signals. After that we have input output oblique memory read write. Here we have shown with the arrows which pin is input pin and which is output. Interrupts are input pins, interrupt acknowledges output, it is active low, hold is input pin, hold acknowledge output pin. Then high order address bus unidirectional, these are output pins, address and data bus, these are bidirectional. Then address latch enable, S1, S0 status signals, input output read write, they all are output signals. Then we have reset out, clock out, these are output signals. At X1 and X2 crystal oscillator of 6 megahertz frequency is connected, which is internally divided by 2. 8085's operating frequency is 3 megahertz. The pins on the chip can be grouped into 6 groups: address bus, data bus, control and status signals, power supply and frequency, externally initiated signals, serial input output ports. The 8085 microprocessor can almost qualify as an microprocessing unit, but it has the following two limitations. The low order address bus of 8085 microprocessor is multiplexed time shared with the data bus. The buses need to be demultiplexed. Appropriate control signals need to be generated to interface memory and input out with 8085. Demultiplexing AD7 to AD0. The low order address bus AD0 to AD7 lines are serving a dual purpose, and that they need to be demultiplexed to get all the information all time. The high order bits of address remain on the bus for 3 clock periods. However, the low order bits remain for only 1 clock period, and they would be lost if they are not saved externally. Also notice that the low order bits of the address disappear when they are needed most. Demultiplexing. To make sure we have the entire address for the full 3 clock cycles, we use an external latch to save the value of AD0 to AD7 when it is carrying the address bits. We use ALE signal to enable this latch, address latch enable signal. That is, given that ALE operates as a pulse during T1, we will be able to latch the address. Then when ALE goes low, the address is saved and the AD7 to AD0 lines can be used for their purpose as bidirectional data lines. High order address bus is unidirectional. Here we have low order address and data bus, that is multiplexed. Here we have to separate address bus and data bus. Here we use address latch enable pin. Here signal at first clock cycle becomes high, after that it becomes low. Whenever it is high, this latch is enabled and the address information is stored in these latches and available all the time. And now after the first clock cycle we can use this AD7 to AD0 as our data bus. Generating control signals. 8085 generates a single read signal, however, the signal needs to be used with both memory and input output. So, it must be combined with the input output oblique memory signal to generate different control signals for the memory and input output. Here we have used various gates to generate 4 control signals from 3 pins, 3 signals, that is input output oblique memory. They are combined with read write to generate memory read active low signal. After that input output oblique memory is combined with write to generate memory write. Then input output is combined with, after inversion it is combined with read to generate input output read and input output write. How a stored program is executed. The starting memory address is transferred into the program counter. Now microprocessor execute the program as given below in 2 cycles, one is fetch operations, then is execute operations. In fetch operations, the microprocessor will transfer 16-bit address from program counter to address lines, so desired memory location is selected. Microprocessor then gives reading location, read low. So, 8-bit instruction code is transferred from selected memory location to data pins. This instruction code is transferred by microprocessor from data bus to instruction register. Then execute operation. The instruction code is transferred from instruction register to instruction decoder. The instruction decoding unit decodes the instruction and provides information to timing and control unit to take further actions. If the instruction code is of 2 or 3 bytes, then the circuit will read second and third byte of the instruction from memory and then execute the corresponding instruction. Then cycles and states. T state, one subdivision of an operation. A T state lasts for 1 clock period. An instruction's execution length is usually measured in number of T states, that is clock cycles. Then we have machine cycle, the timing required to complete one operation of accessing memory, input output or acknowledging an external request. This cycle may consist of 3 to 6 T states. Then instruction cycle, the time required to complete the execution of an instruction. In 8085, an instruction cycle may consist of 1 to 6 machine cycles. Then important questions from this chapter: why address bus is unidirectional in 8085? The address bus is unidirectional because address information is always given by microprocessor to input output devices and memory. What is Intel 8085 used for? The purpose for 8085 is of computing. Why were 8085 microprocessor given that name? In 8085, 5 means the microprocessor operates at 5 volt, third 8 means 8 bits, is its word length is 1 byte, it is a name to identify chip. Why multiplexing is used for data and address bus? Multiplexing of data and address buses is done to reduce the pin count of the microprocessor chip. Which stack is used in 8085? Last in first out stack is used in 8085. In this type of stack, the last stored information can be retrieved first. What are hardware interrupts? Trap, RST 7.5, RST 6.5, RST 5.5 and interrupt request. These are the 5 hardware interrupts. What are the software interrupts? Restart, RST 0, RST 1 up to RST 7. These 8 are software interrupts. What is meant by a bus? A bus is a group of conducting lines that carries data, address and control signals. What is the purpose of registers? The purpose of registers is storage. What is the RST for trap? RST for trap is RST 4.5. What is the block diagram of 8085 microprocessor? The block diagram of 8085 shows the signals flow of the 8085 architecture. It is a way to know where you have specific memory, input, output, etc. Thanks.